Today, I am going to talk to you about concrete which can be manufactured with carbon-based agricultural byproducts, which will make concrete highly sustainable. But we will also add a little bit of carbon structure nanomaterials. Because if you look at the title, we are targeting a carbon negative concrete that it's not only carbon negative, not carbon neutral, but carbon negative concrete this time. Not only carbon negative, but also the mechanical properties will be greatly, I will show that we can greatly enhance them. So what is of very interesting to just, I'm probably recapping because we have heard that during this conference, is that concrete is obviously a material with very high CO2 emissions. You can see that. Unfortunately, I cannot use the pointer. It's okay. To show you exactly what I'm talking about. The emissions are approximately 600 pounds per cubic yard, and these are mainly due to the high, very energy intensive manufacturing of process of cement. We can show that concrete has a potential for sequestration, for CO2 sequestration. By the term sequestration, we refer to CO2 uptake and CO2 mineralization. And so many speakers during the first session showed the potential of CO2 mineralization with using different pathways in concrete. But still, the capacity of concrete for CO2 sequestration remains low. So while the emissions are about 600, the total capacity of concrete sequestering all the carbon dioxide from the atmosphere gives us a total of 360 pounds per cubic yard. So there is room available for improving these numbers if we want to make it neutral, and people had shown during the first session how we can make it neutral. I'm going to show you a second approach of go a step further, make it negative. The problem that we are all facing in this field right now is that we need to find a way to overcome the low diffusion CO2 properties in concrete from the environment. And if we manage to overcome this problem, then we may be able to find great ways for enhancing the CO2 capture and mineralization in concrete. So one of the indicated ways right now, and very popular, is the use of porous materials. Now, in the picture, in this slide, I'm showing a highly porous material, which is comes under the name Biochar. It's an agricultural byproduct, is actually a byproduct of also used by the factories that they produce graphene from and the agricultural byproducts. It's mainly carbon, contains a little bit of carbon of carbonates, but very small amounts. And if you consider the structure, the unique 3D porous structure of the material, it's not a nanomaterial, obviously. It's you see there the scale is really big, but this unique 3D porous structure provides channels, if we include them in concrete, that can help accelerating the CO2 diffusion. So this was a concept that we examined, and its potential can be about 15 to 25%, which is way higher than the potential of the ordinary Portland cement concrete. So we started using this agricultural product, biochar, not only to accelerate the CO2 uptake and mineralization, but also to create a sustainable product within the framework of today's scientific, let's say, interests, how the material can be more sustainable. What you see in this slide is our experimental program. We created specimens using biochar. The biochar will obviously, before, I mean, this is not the preliminary work that we are doing with the biochar. We have already concluded that the optimum amount is 1%. I can go higher, but then I create many other problems. So we went up to 2%, we went up to 3%. We didn't like what we see, so we got stuck with 1%. The material has huge potential, and we used it in fabricating specimens, accelerated CO2 curing, and measured CO2 uptake, mineralization, and the mechanical properties. We evaluated the CO2 diffusion using FTIR and TGA tests. The results of the FTIR I'm showing in this slide. I'm showing the typical FTIR spectrum of carbonated specimens. Dr. Danoglidis showed this in the previous presentation, in the previous session. What I'm showing here, interestingly, is I have reverted the graph, and now I'm showing the transmittance, not the absorbance. Dr. Danoglidis was showing the absorbance in the FTIR. So I flipped the graph, the typical graph. Still, we are obtaining the major peaks that can be found using the FTIR. For example, the peaks at 870 and 9064, I believe, are associated with the silicon-oxygen bonds that Dr. Danoglidis explained. And the peaks at the 3380s and the 3640s are due to the hydroxyl groups in water and calcium hydroxide. Now you see a long stretching vibration of the carbonate ions at 1370 that indicates the existence of the calcium carbonates. And we use the intensity of the transmittance of this characteristic peak to evaluate the CO2 diffusion in concrete. Low transmittance values indicate higher CO2 diffusion within the sample. So now I am comparing two samples. I am comparing a mortar, plain mortar, and with a mortar that was fabricated with 1% biochar. Again, that 1% was selected from our preliminary study as the best performing proportion, not in terms of CO2, but in terms of mechanical properties. Don't forget that this is an agricultural product. It contains impurities, and we are replacing cement. So 2%, we are removing 2% of cement, then the properties change completely. So we measured the CO2 diffusion. Diffusion in concrete depends on the kinetics from the surface to the interior of concrete, obviously. And we assessed the FTIR spectra. We measured the transmittance at the center of the cross-sectional areas of our prisms, with approximately 2 centimeters from the surface. Now, the CO3 characteristic peak that you see at the 1370 wavelength pink for the plain mortar, you see that it's around 62, which, I'm sorry, for the carbonated, it's around 62, and this indicates a very high CO2 diffusion, so within the concrete matrix, so results were very encouraging from this initial test. Because if you compare it with the peak of the plain mortar, obviously this one is much higher. And plain OPC mortar indicates, has a very low CO2 diffusion capacity. I would like to show you a picture, an SEM picture of the biochar, just to show you that the channels that were created inside concrete due to the biochar. If you see, we highlighted them with the yellow line, and this is what we are talking when we mentioned the concept of increasing the porous channels so that we can attract more CO2. Oops, it's not responding very well. TGA, we use always TGA to measure the CO2 uptake and mineralization according to the very well-known procedure. And then we were able to quantify this. You see a comparison here of the CO2 uptake and mineralization. Of CO2 uptake and CO2 mineralization, we're talking about the same index. It's nothing different. It's just that with the mineralization, we are essentially measuring how much carbonates we can consume within the formation, during the formation in the cementitious matrix. Well, there is no comparison between the two materials. Obviously, using biochar, we are able to attract more CO2, diffuse more CO2, and increase the mineralization capacity of concrete. 1% per weight still. I can show you many other results increasing the amount of biochar, which is very promising. But before I do that, and before we talk about this, let's talk about the mechanism. What you see in this picture is the calcium carbonate crystals that were formed inside these channels. So apparently, porous pathways that can accelerate the precipitation of carbonates, and we were able to identify all the forms of the carbonate crystals, hexagonal, cubical shaped, in like I'm showing you in the picture. But don't forget the initial question that I indicated in the beginning of my presentation. I want to create a carbon negative concrete. So how much biochar does it take to create a carbon negative material or a carbon neutral material? So now that I used 1%, because 1% I liked from the mechanical properties that it was giving me, let's see what it's giving me in terms of carbon, let's say, emissions. So in this slide, the right part, you see the CO2 emission sequestration, the numbers after 28 days of carbonation, and from the calculations you will see that the biochar mortar exhibits a slightly higher CO2 sequestration capacity, which leads to a total removal of CO2 of about 5 pounds per cubic yard. Now, biochar concrete can be considered like a carbon neutral material. I can say that safely, but the question here is, it's not a carbon negative material. So using biochar, we can definitely create a carbon neutral material. But I wanted to create, I'm a little bit greedy, I wanted to create a carbon negative material. So now the next question is, do we do what? Increase the porous pathways? We have to find if increasing the proportions of biochar can help, which I'm telling you it does not, in terms of mechanical properties, but we can use it for CO2 sequestration if we are willing to compromise the concrete's mechanical performance, or we have to find another way. Now, the whole project that we submitted to NSF, the idea was that maybe we can combine the two ideas, that we can take a good use of porous surfaces, including porous channels in concrete, to increase the CO2 sequestration in a similar way like we can use almost recycled aggregates inside concrete. That would also give us some porous pathways, and also at the same time find a way of accelerating, enhancing the hydration kinetics, but this is a job of the nanomaterials. Now, nobody else can do it. Now, we decided to use a few graphene nanoplatelets. Dr. Danoglidis showed the effect in the previous presentation and the mechanism of the graphene nanoplatelets in concrete. If we exfoliate the graphene nanoplatelets into tri-layer graphene layers, then the dosage of graphene is very low. It's 0.3% per weight per volume, which corresponds to 0.15 per weight of cement. Then we can increase the CO2 uptake and mineralization by 28%. Don't forget that with the biochar, we managed to increase it at 50%, right? So biochar is definitely doing a better job than graphene. But the question here is, maybe they can work synergistically. So this is the right question right now. If we can combine to produce biochar graphene engineered concrete, so that we can enhance the CO2 uptake and mineralization. And here are the results, using the exact same procedure that we have an accelerated carbon curing chamber that we use for our experiments. So results speak for themselves. Mortar has a 17% uptake, CO2 sequestration, let's say, capacity. Adding graphene nanoplatelets, we can increase that to 20%. Adding biochar to the plain mortar, we can increase it to 57%. But adding both together, we can increase that to almost 90%. So this is a very exciting result. And we decided to go with this particular recipe. In terms of numbers, after 28 days of carbonation, we can see that the engineered concrete is leading us to a total CO2 removal of 55 pounds per cubic yard. Now, this is a carbon negative material, not the biochar by itself, which, if you remember, it was 5 pounds per cubic yard. In terms of mechanical performance, very exciting. Modulus of elasticity. With biochar, we do not expect, obviously, to have exciting results only with using biochar. But if you enhance it a little bit with some graphene nanoplatelets, we can reach, let's say, an increase of at least, what was that, 15, 16, and then we went to a modulus of elasticity of 18. 2 gigapascals increase. Ductility, that's the interesting thing. This is not the modulus of elasticity. We can do way better to the modulus when we're using carbon fibers or carbon nanotubes. But with graphene, what is very, very encouraging is that we can, after evaluating the material's strain energy absorption capability, we found out that the flexural toughness of the material, calculated by the load CMOD curve in fracture mechanics experiments, we were able to increase the flexural toughness by approximately 200%. So this is very encouraging because carbonation leads to a more brittle material, usually, right? But in this time, with a combination of nanomaterials and the biochar, we were able to increase the toughness, yet not change the brittleness of the material. So I know that I have already spent 20 minutes talking, and my co-moderator here today is very angry at me. So I would like to conclude. My presentation about our results. So obviously we can have an engineered matrix that will exhibit higher CO2 diffusion kinetics, which is what we targeted in the beginning, managed to increase the CO2 storage and mineralization about 90%, which is something that we were not even expecting in the beginning, and create what we call a carbon negative concrete. But it requires the combination of porous channels through a highly porous material such as biochar, still carbon-based material, and a nanomaterial that is providing the big surface area such as the exfoliated graphene nanoplatelets. Thank you very much for your attention. Please, I'm open to any questions if we have time.